Hello. In this lesson, we will cover the fundamentals of hierarchical clustering. The focus will be on the core conceptual framework and the types of problems you are likely to encounter on the exam. Let's get started. Hierarchical clustering is a method of cluster analysis used to group common data points together. Unlike k-means clustering, which requires the number of clusters to be specified in advance, hierarchical clustering does not require you to know the number of clusters ahead of time. This makes it valuable when the optimal number of clusters is unknown. Hierarchical clustering produces a tree-like diagram called a dendrogram. Let's see what that looks like. A dendrogram records the sequence of merges. The vertical height of the branches indicates the level of dissimilarity. Assuming the same scale, the higher the merge, the more different the clusters are.
The most common approach is agglomerative or bottom-up clustering.
We start with every single observation as its own tiny cluster, and then we start fusing them. Dendrograms don't have to be symmetric. Here, 4 similar observations cluster tightly, while one outlier joins much later at a greater height. Here's another example. A chaining pattern where observations on the left join one at a time, while 2 on the right pair up early. This kind of asymmetry is common with single linkage, which is a linkage method covered later in the video. In terms of the algorithm, the process begins by treating every data point as an independent cluster. For a dataset with n observations, we first calculate the dissimilarity between all possible pairs. Next, we iteratively identify the 2 clusters with the smallest dissimilarity and fuse them into a single cluster. After each merge, we update the dissimilarity matrix to reflect the new cluster structure. We repeat this process until all observations are joined in one final cluster, forming the complete dendrogram. Don't worry if this algorithm seems abstract right now. We'll go through an example later. But first, we need a method to evaluate the dissimilarity between clusters of data points. This is where linkage methods come in. There are 4 primary linkage methods covered in the text: complete, single, average, and centroid. Each of these methods differs in how they measure intercluster dissimilarity. Intercluster dissimilarity refers to a measure of how dissimilar observations in 2 different clusters are from each other. With complete linkage, the intercluster dissimilarity is the maximum distance between any observation in one cluster and any observation in the other. This tends to produce more compact, spherical clusters, but is sensitive to outliers. For single linkage, the measurement is the minimum distance between any pair of observations across the 2 clusters. Single linkage tends to produce long, chain-like clusters. Average linkage uses the mean of all pairwise distances between the 2 clusters. It provides a balance between complete and single linkage and is less sensitive to outliers. The centroid method compares the centroids, or centers of mass, of the 2 clusters. It provides a different perspective on cluster similarity, but is prone to inversions, where clusters are fused below either of the individual clusters in the dendrogram. Here is what an inversion looks like. In a normal dendrogram, each successive merge occurs at a greater height, but with centroid linkage, a later merge can drop below an earlier one. The red branches show clusters C and D merging at a lower height than the earlier AB merge. This reversal is called an inversion. Let's work through a numerical example to illustrate these concepts. Consider 3 observations: A at 1, 2, B at 2, 3, and C at 5, 8. Suppose A and B have already been merged into a cluster. Let's calculate the distance between this cluster and point C using the 4 linkage methods. We will use the Euclidean distance in this example. This is the most commonly used distance metric, and the metric that is likely to show up on the exam. In 2-dimensional space, the Euclidean distance is defined as the square root of the sum of the squared differences in the x and y coordinates. It effectively measures the straight line distance between coordinates. First, let's calculate the Euclidean distances between the points. Between A and B, it's the square root of 2. Between A and C, 4 squared plus 6 squared gives us the square root of 52. And finally, between B and C, 3 squared plus 5 squared is the square root of 34. In single linkage, the distance is defined as the minimum of the pairwise distances between the clusters. In this case, it is the minimum of the distance from A to C and B to C. Comparing the square root of 52 and the square root of 34, the square root of 34 is the smaller value. This gives us the single linkage distance. Complete linkage takes the maximum distance between points in the two clusters, representing the most conservative estimate of dissimilarity. Between the square root of 52 and the square root of 34, the max is the square root of 52. Average linkage computes the mean of all pairwise distances between the two clusters. Here, we take the average of the distance from A to C and from B to C. Substituting the values and computing the result, we get approximately 6.52. For centroid linkage, we first determine the centroid, or the average position, of cluster AB. The midpoint of 1, 2 and 2, 3 is 1.5, 2.5. Now we calculate the distance from this new point to C. Computing 3.5 squared plus 5.5 squared gives us the square root of 42.5, which is also approximately 6.52. We can now compare the results of the different linkage methods. Single linkage resulted in the smallest distance, while complete linkage yielded the largest. Average and centroid linkages produced intermediate values. In this final section, we'll finish up this video by running through the full algorithm on a dataset with 9 observations. On the left, we have our data in feature space. On the right, we will build the dendrogram. Initially, every point is a cluster, but we fix that by merging the most similar ones first. 4 and 6, 3 and 8, and 2 and 5 are very close, so they merge at a low height. Next, we check the distances again. Point 1 joins the 4 and 6 group. 9 joins 3 and 8, and 7 joins 2 and 5. The dendrogram grows higher because the dissimilarity is increasing. Now we continue to merge whole clusters. The group with 1, 4, and 6 merges with the group containing 7, 2, and 5, since they are closest. Finally, the last 2 massive clusters merge at the very top. All observations now belong to a single cluster. One note about the x-axis labels before we move on. The horizontal position tells you nothing about distance. 8 and 1 are far apart in distance, but are next to each other in the dendrogram. And that is hierarchical clustering in a nutshell. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.